Good afternoon, everyone. Today we are going to conduct a experiment from our advanced control laboratory for your laboratory class, that is belongs to the course 6372 advanced control lab. Our experiment here regarding the system identification toolbox of Matlab. Now we will use the system identification toolbox of Matlab to estimate a transfer function model of a inverted pendulum system which is denoted by a real-time model, and the real-time model is provided by this company feedback. This is the real-time model. This is our real-time model console. Now we will use this console to go for our further steps for the identification of that system. Now our system is inverted pendulum. We can see this is our practical setup of our inverted pendulum. Now this inverted pendulum, our job is to stabilize this inverted pendulum. Now from the general point of view, we know this system is a very unstable system. So identification of this kind of system is also very hard. Or basically whatever mathematical modeling we are proposing, those are not accurate to this model. So what we will do, we will extract the data from this real-time model to our Matlab environment. Then from that data we will estimate a model using the system identification toolbox, and in the further cases we will try to design a compensator which can compensate that basically we try to design a stabilizing controller for this inverted pendulum system. Now for this case we can see first step, whenever you are try to design a controller using system identification toolbox, first you have to do the identification. So for that identification we can see there are a lot of boxes here provided by this company. So what we will do, we will use this invert pendulum ident. So by clicking this box, you can see here new window will be open. Now from this window we have to run this window. If we start running this window, this computer will give a command to this real-time model and it will run arbitrarily, and it will give a data from this time period. We can see here it is just a simulating environment. So whatever time period you want you can give. Suppose we are giving a 40 seconds of time lapse. We want to see within this 40 seconds how this inverted pendulum is behaving. Just behavior you are collecting. So those data will be go to that C mount block here. We can see here in this model, this is the C mount. So whatever vectors is manipulated in this C mount block, you can see here this angle, the control input, the position, the time, and the excitation is coming. These all, that means the control inputs, these all are going to this C mount block, and this all data will be available in our Matlab workspace, and we will use that data to design a model or to estimate a model according to that behavior of that system, and the behavior can be reflected by this data. So our first job is to run this model. So it is not directly we can run this model like any simulating model. Because of this is a hardware model, we can see here this is the mode of this running model is external, and to run this model first to build it. So for that case we click on that thing, so directly it will build that model. So it is built, we can see it is ready. Now whatever commands we want to give to this thing, first you have to connect this hardware to this computer. So for that case, so we can click on this thing, so it will connect it to the target. Now we can see now it is ready to run. Now if you click on this start button, it will run that real-time model, and it can be shown in the hardware how the commands has been interpreted. So we will show that thing. So closely look at this point. So we are running. So it is start running. Now we will switch on the start button. Now you can see the behavior here, and not only here also a scope has been seen here. So in this scope, three things has been shown here: the position, the angle, and the control inputs. So you can see here, so this is the case, and we will also see. So this is how the pendulum is behaving according to this model input. Now we will wait until the 40 seconds has been collapsed. So you can see here 40 seconds completed, and now we are ready to collect the data because the 40 seconds has been completed. Now we can see here in the Matlab environment there is a variable in that workspace named as cmount. So we will use, if you double click this thing, you can see there are total 5 vectors, 1, 2, 3, 4, 5. So we have to choose what is the input of the system and what is the output of the system. Before using your system identification toolbox, you have to know the input and output sequence of your original physical model. For that case, we have 5 vectors. So from those we have to choose the control input and the interest of variable. That means what are the variable we want to control. That is our output. So for that case, you can see from your pendulum model, you can see. So this is the angle. So because of we are only concentrating on the inverted pendulum stabilization problem, so our output must be the angle. And what is our control input? The control input is the last one, is our control input. So we will collect the first vector and the last vector. That means the first and the fifth. These two vectors we will collect to design our system identification estimated model of this real-time system. So how to collect? So we can easily collect by this Matlab and in this Matlab environment. So what we can do, we can create two new variables as u and y. So what is our u? Our u is equal to, it will be our last and the most vector. So you can see here, this is how your u has been created, and our output is our first vector, that means our angle. So this is our u and y collected. One thing to remember, whenever you create these two vectors, the input and output, the size of these two vectors must be same, otherwise ident will not work. The system identification toolbox will not work, it is failed to estimate. So now we will call the system identification toolbox. To call the system identification toolbox in Matlab, there is a simple code. You can write ident only. If you write ident and enter, hit enter, you can see the new toolbox has been opened. So this is the main interface of the system identification toolbox. Now what first we have to do? First we have to import data on this environment. So for importing data, you can see in left here the import data option is there. So from that sense, we just simply import data. So our data is in time domain, so we will collect the data in time domain. So it will be a time domain data. Now it will ask for the input and output. What is our input? Our input is u and our output is y. Remember, if you don't create these two variables in your workspace, that means if it is not available in workspace, because what it is so workspace variable, so it will not work basically. And another thing to remember, this sampling interval. So it is up to you that how many seconds you have run and how much in which point you want to collect the data, or the time interval. That means if you want that sampling time to be very low, then the data will be very good. So we have an optimal point in our, we have conducted lot of time this experiment, so we know a value that we can give for this kind of model. So we choose suppose 0.001 as a sampling interval. Okay, so our data has been imported and it is reflected in this my data variable. Now if you want to see that how this data has been incorporated in this system identification console, so there are a lot of options there. Suppose we want to see the time domain plot. So this is the time domain plot of our imported data. So this is nothing else but the behavior of the data only. By this system identification toolbox is incorporated this data. Okay, so this is our input and this is our corresponding angular position output, that means the pendulum we want to stabilize. Now we want to estimate a model according to this data, according to the, suppose we run it for 40 seconds. So in 40 seconds, how this system is behavior, that means the dynamic behavior of the system can be shown by the system identification toolbox. For that case, we have to estimate a model. So for that estimation, there is a option here in the system identification toolbox, estimate. So if you click on the estimate, there are a lot of options there. Linear parametric model, process model, nonlinear model. There are a lot of options there. Now because of we try to design a controller, so we want to stick on linear parametric model. That means in a linear model, it may be state space model, linear, it may be a transfer function domain. So we want a linear parametric model. That is why we choose a linear model. Now once we click the linear model on the system, so once we click that linear model in the system, there are another type of pop-up will come. In this pop-up, you have to choose the targeted linear model you want to estimate from this given experimental data. It may be different form. So what form you need, that is up to the designer, or it may be on the experience, or it may be from the mathematical model. So it may be anything. So the structure of our desired model can be formed by this different identification structure. So suppose in this ARX structure, RMARC structure, these all structures has been available. So you can use any of them. Now there is a restriction to choose this kind of structure. So what is the restriction? We will show it. What are the restrictions? Suppose we choose OE. So here we have chosen OE structure. Now from this OE structure, after OE structure, you have to choose what should be the model order of you, what should be the order of your targeted model. So we have, again, we previously shown, we have conducted this experiment plot of time, and it is just a demonstration of our system identification real-time model. So we know what kind of order is needed for this kind of system. Suppose we choose 3, 6, 1. So we choose 3, 6 and 1. So after choosing this structure and order, now we can able to estimate our linear parametric model. Suppose if we click on the estimate, so it will clearly estimate the model. It will take some time and it will estimate the model according to our input. Now you can see, so this is our input block, so this is our output block of our system identification toolbox. So you can see this OE361 is now available. Now we want to see that how this OE361 is behaving. That means our targeted model is how it is behaving. Is it same as the practical data or not? For that case, you have to see this thing. That means this model output. Again, if we can see this model output, so this is the feed value for our estimated model. So you can see there is a lot of difference between our estimated model and our real-time model. So, and the feed value is showing as 9.148. So until and unless this feed value goes very high, above 50% or 60%, whatever controller you are designing, the controller will not be applicable to your estimated model, because you have wrongly estimated your model. Maybe overestimate, maybe underestimate. So the whatever control action will go according to the overestimated or underestimated model to your real-time system, it will every time fail. So your duty is to ensure that estimated model must have a best fit value, and the best fit value must be beyond 50 to 60%. It may be this 9.148 must be 50 or 60. Until and unless you get such kind of a model, you cannot implement your PID controller to this system. So this is your job to make this feed value high. So for those cases, we can try several things. We can try rather than more models. Suppose we try OE221 and try to see how this thing is behaving. So the performance is decreased. You can see here it is decreased. So previously it was 9, now it is 5. So it is a more worst estimation rather than the previous one. So again we can go to this mode again, and suppose we choose, let's just go. Suppose we choose a first order model. Then we try to estimate. So again this is a more worst performance. So by this way you can try lot of methods, lot of models you can try. Here lot of structure also you can try, but we want to stick on this OE model only, because we want to form a transfer function from this thing. So that is an ordinary differential equation model, and it is linear basically in mode. So linear parametric model, and it is easy to determine the transfer function from this structure. So suppose we want to increase, suppose we want to fourth order model. Now we will see what can happen, because we know if we make the order, now you can see the fourth order model is it is giving better result from the previous 3 estimation. So in this way you have to make it increase. This is the one way. Another way is to run that original real-time model for more time. Suppose here we have run for, what is that model, sir? Pendulum model. Suppose here we can see previously here we run the model for 40 seconds. It doesn't mean you have to run for 40 seconds. You can run it for more seconds. You can run it for 400 seconds or 100 seconds. If you give more time to this thing, the data will be more pure and the estimation will be more good. So it is just a simple demonstration of our system. So when you come back to our laboratory, you can try several things from this system identification toolbox. So today our goal is to show how you can use this tool to estimate a real-time model and give a glimpse to design a compensator or a stabilizing controller for this inverted pendulum system. So from the system identification toolbox, we have given the targeted model structure and the targeted model order from this thing. So we have compared, and this lot of comparison we have done, lot of structure and order we have considered. So now what we want to do, if we want to go one step further, suppose you want to design a PID controller. To design a PID controller, you need a model, that means one transfer function model or state space model. So this structure will not give you directly the transfer function model. For that case, what the system identification toolbox has given another option. What you can do, you can directly move this structure, this output structure of this system identification toolbox to the workspace. How? By dragging this two workspace block. So we can drag any of them. Suppose we want to drag this 661. So if you drag this 661, then minimize, and then you go to the Matlab, and then you see to the workspace. So you can see in the workspace this OE661 is now available. Now our estimated model from the system identification toolbox is available on our workspace. Now we can able to design the transfer function from this targeted or estimated model. How to do this thing? So just it is simple. Just you create a variable for your targeted open loop transfer function of this model, which is G. Suppose I have taken as G. Then for the transfer function, what is the command? That is TF. So under in the TF, so you put your workspace variable targeted model. The targeted model variable which is shown in our workspace, which is OE661 that we have already dragged. So if you click this thing and hit enter, it will give a discrete time transfer function model, or so you can see here it is giving a discrete time transfer function model of 6th order system. Now again, whatever tools available in Matlab to design a PID controller or compensator like CISO tool, so this kind of system will not work with this discrete model. So we have to go to this S domain, that means the continuous domain model. For that case, we can use that D2C command. That means the digital to continuous domain conversion of your transfer function. So you have to create another new variable, suppose G2. So G2 will be your new transfer function, which will be converted from your digital version to your continuous version, and your previous digital version transfer function is G. So if you click on this thing, now you can see this is your, basically this whole thing is your targeted model, real-time model, transfer function created by your system identification toolbox. Now you use this transfer function as an open loop model of your inverted pendulum. Then you design a PID controller from this transfer function. Once you have successfully designed that PID controller according to your system performance index, then what is your duty? Then your duty is to stabilize this inverted pendulum by putting your PID values. What if from that thing, now you don't have to go to the ident, now you have to go to the control. So for that case, this is the control. This control is not also this control. So this swing hold pendulum control is there. So in that case, this is your inverted pendulum stabilization. So you can see there are two controllers available. One is for your position, another is your cut basically, and another is for your angle. So the angle part has been done, and for the cut part you make it remain as it is. So in that angle part, if you click on this PID block, you can see there are three values has been showing PID. So these three values will now be available from your design parameter, and you will put these values here and then make it okay. Suppose I am running this model, I want to see how this is happening. So again the same thing, first build, once it is built, then you connect. Once it is successfully connected, then you run. Now to see the behavior, you can see to the scope. So it is a stabilization problem we are solving. So if you can successfully design a PID controller, the behavior will be such like that. It can be shown here. So now the control action is over, that is why it is gone. Okay, thank you.